Welcome to Lodestar Library. Today, we're diving deep into a fascinating topic. We are going to build a really detailed mental model of how large language models actually work from the ground up. We're taking what honestly feels like pure magic and turning it into a structured, highly detailed tutorial. We'll explore the literal, physical anatomy of how we build these incredible machines.
And hey, it's a completely fascinating paradox, right? These systems can tackle PhD-level physics, chemistry, and biology without breaking a sweat, but they totally fail at counting the R's in a simple word like strawberry. Why does an AI that seems so brilliant suddenly look, well, remarkably foolish? Stick with me, because by the end of this tutorial, you are going to know exactly why.
All right, so here is our quick syllabus for today's tutorial. We'll cover 1. Pre-training the base model, 2. Tokenization and neural networks, 3. Post-training the assistant, 4. Understanding LLM psychology, and finally, number 5, tools and better prompting. Let's jump right into section 1, pre-training the base model, or how we go about scraping the internet. So to build that initial base model, developers have to download and aggressively filter the raw HTML of the internet. They're basically weaving this massive tapestry of text data. To put this in perspective, high-quality datasets like FineWeb contain roughly 15 trillion tokens. 15 trillion! It's all packed into what ultimately becomes a 44 terabyte lossy zip file. It is a massive, incredibly aggressive compression of human knowledge. Okay, moving to section 2, tokenization and neural networks, the atoms of AI. Before we can even feed that giant tapestry of text into a neural network, we got to chop it all down into a one-dimensional sequence. Now, the absolutely crucial point to understand here is that models do not actually see human letters. They only process mathematical tokens. So a token is basically the fundamental atom of text. It could be a word fragment, a single syllable, or even just a space. Out of a set vocabulary of around 100,000 unique IDs, when you type "Hello World," the model literally just sees a specific sequence of numbers. Right, so once we have our tokens, they flow straight into the neural network. As the network trains, its billions of internal parameters act kind of like the knobs on a DJ set. Picture them being carefully and constantly tweaked until their statistical predictions perfectly mimic the patterns of all that internet text we fed it. Basically, the model is just trying to guess the next token in the sequence over and over again, tweaking those knobs every single time it guesses wrong. Which brings us to section 3, post-training the assistant. This is where we create a truly helpful entity. To really see how the magic happens, we need to look at the stark contrast between a raw base model and a refined assistant model. A base model, it's essentially just a stochastic internet document simulator. If you ask it what is 2 plus 2, it might just spit out a bunch more math questions because it's blindly imitating internet forums. An assistant model, on the other hand, has been fine-tuned to explicitly answer your questions. It's carefully programmed using very specific example data sets created by human labelers. You can think of this entire pipeline kind of like school textbook learning. Pre-training is like reading the exposition. You're just absorbing all that background knowledge. Then, supervised fine-tuning provides the worked solutions. It shows the model exactly how an ideal, helpful assistant should behave. Finally, reinforcement learning forces the model to actually solve practice problems so it can discover the optimal ways to arrive at the final answer entirely on its own. All right, section 4, understanding LLM psychology. Let's talk about those weird quirks and hallucinations. Now that we've built the physical anatomy, we really need to understand the psychology to figure out why these systems sometimes behave so strangely. Like, if you ask an older model about a completely fake person, say Orson Kovat's, it's going to confidently hallucinate a completely false biography. Why does it do that? Well, because it is statistically imitating the format of a factual answer. It wants to sound confident because the human examples it learned from sounded confident, even when the model actually has absolutely no idea what it's talking about. So, to work around this, we have to understand exactly how an LLM remembers things. A model's internal parameters act as a vague, lossy recollection of the internet, kind of like a book you read a month ago. You get the gist, but maybe not the exact quotes. But the text you directly paste into the prompt's context window, that serves as flawless, immediate working memory. The takeaway here is, if you want the model to summarize a document accurately, do not rely on its parameters. Paste the document right into its context window. And that leads us to our final part, section 5, tools and better prompting, how to properly operate the machine. Knowing how the system thinks allows us to completely change up our prompting strategies. Here is a golden rule for you. Models need tokens to think.
Because an LLM applies a strictly finite amount of computational power per token, asking it to solve a complex math problem instantly in a single token will almost always fail. But if you ask it to write out intermediate steps, giving it the space to think out loud across many tokens, it succeeds. This is exactly why we must lean on external tools to cover the model's natural blind spots. Take the task of counting letters, for instance. The LLM's weakness is token blindness. So instead of relying on its flawed mental arithmetic to count the R's in strawberry, we simply ask it to write a Python script using a code interpreter to find the exact mathematical answer. The same exact logic goes for rare facts. Don't let the model hallucinate. Force it to use a web search tool to pull flawless working memory directly into its context window.
So let's wrap up this detailed tutorial. Remember these fundamental rules. Distribute your computation across multiple tokens by always asking for step-by-step reasoning. Heavily rely on external tools like code interpreters for math and counting. Always provide reference text directly into the prompt's context window. And above all else, understand that this is a statistical token simulator. It is a wildly powerful tool, for sure, but it's one that requires a thoughtful operator behind the keyboard. All of this leaves us looking at the frontier. As these systems learn to practice and reason across thousands of intermediate tokens using massive reinforcement learning loops, what profound, undiscovered solutions might they soon uncover that literally no human has ever thought of before? It's a wild thought. Thank you so much for exploring the mind of an LLM with us today here at Lodestar Library.